Good morning, my dear students. Today I am going to start with the next lesson, that is lesson number 4, capacitors and dielectrics. Today I am presenting my chapter, my class or my lesson in a different way, in the way of presentation. Okay, please try to understand it. So, chapter 4, capacitors and dielectrics. The topics that we are going to study in this are given here. The first topic, behavior of conductors in electrostatic field. Second, electrical capacitance. Third, principle of capacitance. Fourth, capacitance of a parallel plate capacitor. Fifth, series and parallel combination of capacitors. Sixth, energy stored in a capacitor and energy density. Seventh, energy stored in series and parallel combination of capacitors. Eighth, loss of energy on sharing charges between two capacitors. 9. Polar and non-polar molecules. 10. Polarization of dielectrics. 11. Polarizing vector and dielectric strength. 12th. Parallel plate capacitors with dielectric slab. Introducing the lesson, what are capacitors? Capacitors are the devices in which electrical charge can be stored and can be used in various ways. So in this lesson we are going to study the principle of capacitors and their uses. So before studying this, let us talk about conductors and insulators. We have all studied about conductors and insulators. Conductors are those through which electric charge can easily flow, or conductors are substances which allow the current to flow through them, like metals, human body. Now we discuss about metals. In metals, the charge that can flow is the electron, that is the only negative charge, that is mobile. Protons are immobile. So free electrons that represent the metals are the carrier of charge. The current in metals flow only because of free electrons. In electrolyte or electrolytic conductor, both positive ion and the negative ion are the charge carrier. So the current flows because of the drift of electrons in the external field in electrolyte, in the external circuit, and inside the liquid or inside the electrolyte, the current is flowing only because of the positive or the negative ion to the opposite terminal. Then next we come out to insulators. Insulators are those substances through which electric charge cannot flow. They have negligibly small number of free electrons, or rather they don't have any free electrons. Examples: glass, hard rubber, plastic, ebonite, mica, wax, paper and dry wood are insulators. These insulators are also called dielectrics. Okay, dielectrics do not conduct electricity. So when these dielectrics are placed inside the electric field, induced charge appears on the surface of the dielectric. Thus the dielectric transits electric effect but do not conduct electricity. So the basic difference between dielectric and insulator is that they do not allow the current to flow, but they transit electric effect. So now we are talking about the effect of a conductor when placed inside the electric field. So the electric field intensity in the interior of a conductor is 0. That is, inside the conductor the electric field is 0. How? When you are placing a conductor inside the electrostatic field, the charge develops inside the conductor on the inner wall of the conductor. So when a conductor is placed in an electric field, the charges drift towards the positive plate, leaving the positive core behind. That is, the at an equilibrium the electric field due to the polarization becomes equal to the applied field. Electric field inside the conductor becomes zero. So when you place a conductor inside the electrostatic field, the opposite charges develop on the outer wall, electrons drift towards the positive plate, and a negative that is towards the negative plate a positive charge is developed, and inside the conductor there is an electric field that is developed. Inside the conductor, net electric field inside the conductor becomes zero. Electric field just outside the charged conductor. When you talk about the electric field outside the conductor is always perpendicular to the surface of the conductor. That is very important point. Electric field is always perpendicular to the surface of a conductor. How can we show this? Let us take the electric field at any other angle other than 90 degree. Then what we have to do? We have to resolve it into two components. E cos theta will be tangential to the surface. Now what will happen? If the electric field is along the surface, E cos theta is the electric field along the surface, then what will happen? There will be a force acting on the electron. As a result, it will start to move on the surface, making a surface current. But we do not get any surface current. So theta equal to 90 and cos 90 equal to 0. So we do not get any current on the surface. Okay, so electric field is not possible at any other angle rather other than 90 degree. Okay, have you understood this? If the electric field is at any other angle other than 90, what will happen? It has to be resolved into two components, E cos theta and E sin theta. E sin theta is perpendicular to the surface, but E cos theta is parallel to the surface, that is tangential to the surface. Now this will accelerate the electron. As a result, the electron will start moving over the surface and will form the surface current, but we are not getting any surface current. Therefore, the cos theta component is not possible. So cos theta, if theta equal to 90, then cos 90 will be 0. So surface current should be 0. Clear? The net charge in the interior of conductor is 0. So when you talk about the conductor, the charges are separated. As you can see here in the diagram, there is a conductor. Positive and negative charge is developed on the wall interiors of the conductor. Let us take the surface integration from Gauss's theorem. Phi is equal to E dot ds is equal to Q upon epsilon naught. Now electric field is 0. E equal to 0. Electric field, we have studied this in the last point. Electric field inside the conductor is 0. Therefore, charge inside the conductor is 0. So what we have learned here? There cannot be any charge inside a conductor. Net charge in the interior conductor is 0. then where does the charge reside? All the charge present on the conductor is always on the surface of the conductor. Whatever charge we are giving to the conductor, it is always present on the surface of the conductor. Suppose a conductor is given some excess charge Q. We construct a Gaussian surface just inside the conductor. So in this diagram you can see that there is a dotted line, that is the Gaussian surface that we have developed inside the conductor. Since electric field inside the conductor is 0, therefore charge inside the conductor is 0. So all the charge is present over the surface of the conductor. Then the last point, electric potential is constant for the entire conductor. We had studied in the last lesson relationship between potential gradient and electric field. So E equal to minus dV upon dr. From that formula we get dV equal to E dot dr. Since electric field is 0 inside the conductor, we put this value, we integrate on both the sides, putting E equal to 0, we get the constant. So what we get? dV equal to 0 or potential equal to constant. So for a conductor, potential is constant. Whatever be the potential, it will be same all over the conductor. The next point, surface charge distribution may be different at different points. Surface charge. Now what does sigma represent? Sigma represents surface charge densities. So at the pointed surface where the point is there, the charge density is maximum. Okay. So sigma surface charge density is total charge over total surface area. So where the surface area is smaller, surface charge density will be maximum. Where the surface is bigger, surface charge density will be less. Now when we talk about a conductor generally has got 3 dimensions. So every conductor is an equipotential volume rather than just an equipotential surface. We start with capacitance of a conductor. Electrical capacitance. The measure of the ability of conductor to store charge is known as capacitance or capacity. Okay. Capacitance of a conductor is a measure of its ability to hold electric charge. When a conductor is given a charge, its potential rises in proportion to the charge given. Q is directly proportional to V. Q is directly proportional to V. More the potential, more the charge that can be stored over a conductor. So we remove proportionality sign. Instead of the proportionality sign, we put a constant. That constant is C, and that is known as capacitance. So Q is directly proportional to V. Proportionality constant C, Q equal to CV. C is known as capacitance or capacity. Therefore C is equal to Q upon V. So we define capacitance. The capacitance of a conductor is defined as the ratio of the charge given to the rise in the potential of the conductor. Once again, the capacitance of a conductor is defined as the ratio of the charge given to the rise in the potential of the conductor. From C equal to Q upon V, it appears that the capacitance of a conductor depends upon the charge given to it or the increase in its potential, but actually it is not so. Capacitance is the property of the conductor of storing charge. Okay, but actually it is not so. Capacitance is the property of a conductor of storing charge. How much charge can be stored by a particular conductor. Now we come to the terms unit of capacitance. So the SI unit of charge is coulomb, potential is volt, C is equal to Q upon V, it is equal to coulomb upon volt, that is 1 coulomb per volt, which is equal to farad, represented by capital F. So 1 farad equal to 1 coulomb per volt. Then we are using smaller units such as millifarad, microfarad, nanofarad or picofarad because 1 farad is a very big unit. 1 farad of a charge of a 1 farad of a charge is equal to 1 coulomb per volt. The capacitance of a conductor is 1 farad if a charge of 1 coulomb raises the potential of the conductor by 1 volt. Dimensions. Dimension of capacitance, it is coulomb upon volt. Dimension of coulomb is current into time AT, and volt is joules per coulomb, that is Newton into meter into upon second, that is m minus 1 L square T raised to power minus 4 A square. So dimension of capacitance is m raised to power minus 1 L raised to power minus 2 T raised to power 4 A raised to power 2. Next we have capacitance of an isolated spherical conductor. We have an isolated spherical conductor of radius r placed in vacuum. Total charge given to the conductor is plus q, that is the sphere holds plus q charge. The charge spreads on the outer surface of the sphere uniformly, so that the potential over the sphere is same. Everywhere the potential is same. Now electric line of forces are emerging out of the conductor perpendicular to the surface, normal to the surface. They are emerging out radially outward from the surface. Therefore, we consider that the whole charge of the conductor is located or concentrated at the center of the sphere. So, total charge Q that was given to the whole surface of the sphere is considered to be concentrated at the center of the sphere. Then the potential at the surface of the sphere is given by the formula 1 upon 4 pi epsilon naught Q upon R volt. So formula for V is equal to 1 upon 4 pi epsilon naught Q upon R. Then capacitance is the ratio of the charge to potential. So C is equal to Q upon V. The capacitance of a spherical conductor is equal to C equal to 4 pi epsilon naught R. So capacitance of conductor is C equal to 4 pi epsilon naught R farad. From this formula, what do you find? 4 pi epsilon naught. These are all constant. Capacitance is directly proportional to radius. The larger the radius, the greater the ability to hold a given amount of charge without running up to high voltage. That is, if you want to hold more charge, greater should be the radius of the sphere. Okay, this equation, this formula C is equal to 4 pi epsilon naught R is true for conducting spheres, hollow spheres, or solid spheres. If the sphere is placed in a medium other than vacuum, then the conductance will become C equal to 4 pi epsilon naught into epsilon R, that is the permittivity of that medium, into radius. Since Earth is a huge sphere, capacitance of the Earth is 711 microfarad. That is why I have told you, when you are talking about the radius of the Earth, it is approximately 6400 kilometer. 6400 kilometer. Then also the capacitance of the Earth is only in microfarad. So 1 farad is a very big unit. That is why we are always using nano or pico or microfarad for a capacitor. If a spherical conductor is placed in a medium of dielectric constant K, its capacitance will be given by C is equal to 4 pi epsilon naught K R farad. That is, the capacitance increases to K times. That is a very important point. If the spherical conductor is placed in dielectric constant medium having dielectric constant K, capacitance increases to K time. Thus, for a given spherical conductor C, capacitance is directly proportional to K. So today we have discussed about capacitance of an isolated spherical conductor. Formula C is equal to 4 pi epsilon naught R. So we will follow the rest in the next video.